This is our third lecture on rotational dynamics. And today, I'm going to discuss about the moment of inertia of few geometrical shapes and also the moment of inertia of a flywheel. So first, we will find out the moment of inertia of a thin circular disc. So let us consider a thin circular disc of mass m and radius capital R. And first, we will be going to find out moment of inertia about an axis through its center and perpendicular to its plane. So if m is the mass of the disk and capital R is the radius of the disk, then mass per unit area is given by total mass divided by the area of the disk, that is pi r square. So mass per unit area is given by capital M divided by pi r square. Now let us consider a small uh, circular strip like this. It is shown there is a small circular strip of radius small r and thickness dr. Okay, so the area of this small circular disk of radius r and thickness dr is given by circumference into the thickness 2 pi r into the thickness dr. So that is the area. So the mass of that elemental strip is given by mass per unit area multiplied with the area of the circular strip, that is m divided by pi r square into 2 pi r delta r, that is equal to 2m divided by capital R square into small r dr. So the given axis is passing through the center of the elemental ring and it is perpendicular to the plane. The moment of inertia about any circular ring about an axis passing through the center and perpendicular to its plane given by mass into a radius square mr square. Okay, that we have derived in the last class. So mr square is a moment of inertia. So here m is 2m by r square into r dr into the radius of that particular ring r square. So on solving you will get 2m by r square r cube dr. So if you assume that the total disk is composed of large number of such elemental strips, then total moment of inertia can be obtained by integrating the above expression between the limit 0 to capital R. Capital R is the radius of the disk. So on integrating and solving, you will get mr square by 2. So this is the moment of inertia about an axis passing through the center and perpendicular to the plane of a circular. Now if you calculate it about the moment of inertia about an axis about its diameter. Okay, so again you are applying the perpendicular axis theorem. Iz is already we know Iz is the moment of inertia about an axis perpendicular to its plane, that is given by mr square by 2, and let us assume that as not assuming it is ix and iy, and whatever be the moment of inertia about an axis, x axis, y axis, or z about any about diameter, about any diameter will be same. So ix iy is equal to I. So 2i is equal to mr square by 2. Then from there you can calculate I as mr square by 4. This is the moment of inertia about the diameter of the circular disc. Now we'll calculate the moment of inertia of an annular disk. This is just a demo picture of an annular disk which is having an inner diameter small r1, outer diameter capital R. So this is the shape of an annular ring. So let us consider an annular ring of inner diameter small r and capital R. That one is just an example. Here we are going to calculate the moment of inertia of an annular disk of small inner radius small r and outer radius capital R. Okay, so the total area of this annular disk is given by pi capital R square minus small r square. That is the area of the annular disk. So mass per unit area is given by capital M divided by pi r square minus r square. So if we consider a small disk of radius x and thickness dx. Okay, so there is a uh, disk which is at of small x diameter and small dx is the thickness. So area of that ring is given by circumference, that is 2 pi x into the thickness dx. So the mass of that ring is given by m divided by pi r square minus r square into the area of that ring is 2 pi x dx. So now again you calculate the moment of inertia mass into the distance radius square. So moment of inertia of this ring is given by 2m divided by capital R square minus small r square x dx into the radius square, that is x square. So again, procedure is same. You just integrate this one to get the total moment of inertia of the ring. You have to integrate this one between the limits small r to capital R. So on integrating and solving, you will get moment of inertia of the disk as annular disk as m by 2 into r square plus capital R square plus small r square. Now we will calculate the moment of inertia about the diameter. So consider two mutually perpendicular axes. Okay, if you consider two mutually perpendicular axes, let IA and IB the moment of inertia about two mutually perpendicular axes. So because of the symmetry, you can say that IA is equal to IB. So by perpendicular axis theorem, moment of inertia about an axis perpendicular to the plane is equal to the sum of the other two axes moment of inertia about two other axes. So I is equal to IA plus IB. So since IA is equal to IB, we can say 2 IA is equal to I. So IA is equal to I by 2, that is given by 1 by 4 r square plus r square. I we have already calculated in the previous case. Now we'll calculate the moment of inertia of a solid sphere. So let us consider a solid sphere of a length L and total mass M, capital M, and let R be the radius of the ring. Okay, so let us we know that the moment of inertia about any axis perpendicular about a circular disk about an axis perpendicular to its plane is given by mr square by 2. So here what we do is we will consider a circular disk like this. Okay, so we can assume that the total cylinder consisting of there are a large number of such circular disks. Okay, so I consider one such disk. Okay, so we consider a one such disk here. Okay, this disk is having a mass small m, smaller disk, circular disk is having a mass m. So the moment of inertia about an axis which is perpendicular to its plane is given by mr square by 2. So if you wanted to calculate the moment of inertia of the cylinder, we need to do the summation for all such cylinders, all such circular disks. So the total cylinder is composed of large number of circular disks. So the total moment of inertia is given by the summation of all that disks. So if you do summation of mr square by 2 r square by 2 into summation over m, then this will give, this is actually not small m, this is capital M. So that is given by m r square by 2. Now calculate the moment of inertia of a solid cylinder about an axis passing through center and perpendicular to its plane. So let us consider uh, an axis which is passing through the through the center and perpendicular to its plane. Okay, so this is any axis which is passing through the center of the um, passing the center of mass. That's this is actually center of mass passing the center of mass and perpendicular to its length. Okay, so the mass per unit length is given by capital M divided by small m. So the for consider uh, small circular disc of uh, um, thickness dy, then mass of the disc is given by m by l dy r square by 4. That is moment of inertia about the diameter, that is m r square by 4. So if you consider a disc, if you consider an axis like this, that will be the moment of inertia with respect to the diameter of the small disc. Okay, so we will calculate the moment of inertia of what that particular axis about the diameter is given by mr square by 4. Okay, a parallel axis theorem, the moment of inertia about any axis which is passing through the center of mass is given by uh, moment of inertia about a parallel axis plus mass into distance square. So the moment of inertia of the disk is given by uh, uh, m, the previous expression mr square by 4l into dy plus the mass per unit length, that is m by l into distance square y square. M by l into dy is the mass of the small circular disc. Then m by l dy into the distance square y square will be the total moment of inertia. So moment of inertia of the cylinder can be calculated by integrating between the limits minus l by 2 plus l by 2. So on integrating and solving, you will get the moment of inertia cylinder as m into r square by 4 plus l square by 12. Next is the moment of inertia of a solid sphere. So you consider a solid sphere of mass m and radius r. Then the mass per unit volume is given by m divided by 4 by 3 pi r cube. That is, volume of the cylinder sphere is 4 by 3 pi r cube. If m is a total mass, that mass per unit volume is given by m by 4 by 3 pi r cube. The first we will calculate the moment of inertia about the diameter. So you consider a small element in this solid sphere, which is at uh, which is having a thickness dy. Okay, and so if you consider a small disk of thickness dy at a distance y from the center, then the radius of that disk is given by square root of r square minus y square. R is the total radius, y is the distance from the center to the small disk which we are considering. So volume of the disk is given by pi r square. R is the radius is given by square root of r square minus y square into dy, that is pi into r square minus y square into dy. So the mass of the disk is given by the rho into uh, pi r square minus y square dy. Rho is nothing but the mass per unit volume, which we have already told. Rho is nothing but mass capital M divided by 4 by 3 pi capital R cube. So moment of inertia of that particular disk which we are considering is given by mass into radius square by 2. So moment of inertia of this disk which is having a radius square root of r square minus y square, and the mass is given by rho into pi r square minus y square dy is given by mass into radius square divided by 2. Okay, so if we wanted to calculate the total moment of inertia, you have to integrate between the limits minus r to plus r. It's a simple straightforward integration. If you integrate this one, uh, so it is rho into this is rho into uh, pi r square minus y square whole square by 2 dy. So this is 1 2 is taken out. Then on r square minus y square whole square is expanded. So r raised to 4 plus y raised to 4 minus 2 r square y square into dy. So integrating with respect to y, the first term will give r square r raised to 4 into y. Second term will give y raised to 4 by 5 minus 2 r square y raised to 3 by 3. So between the limits minus r to plus r. So just apply the limit and solve it. You will get moment of inertia as 2 by 5 m r square. This is the moment of inertia of a circular disk of about the diameter. Now, if you consider the moment of inertia about the tangent, again it's a very simple, straightforward calculation by applying parallaxis theorem. I keep this is the moment of inertia of the axis, tangent axis, and this is the moment of inertia of the diameter. If r is the distance between this, you can calculate the IT moment of inertia about the tangent is given by 7 by 5 m r square. Okay, so next, now we will take the case of a flywheel. So flywheel is uh, a large heavy wheel. This is a wheel. Most of the mass is concentrated on this wheel, and there is a axle which is passing through the center of mass of the flywheel. So it is a device which is having a very large moment of inertia. It is having a very large number of application in industry. That is this is applicable to make smooth running of the machines, because its kinetic energy of rotation is quite high, so it is difficult to stop. So sudden stopping will can be avoided by using flywheel. So the engines can run smoothly for a long time. So this is the theory. So there is a cord is wounding on the axle. There are n times small n times of wounding on the axle. So this is the number of wounds on the axis. Okay, so small r is the radius of the axle, and it makes a, after the detachment of the mass, there is a mass is attached on the end of the cord. So once we release the mass, it will make n small n times rotation. Then after n number of rotations, the mass is detached from the flywheel, and the flywheel makes n rotations before it come to rest. Now we will see the theory. The Actually, the potential energy of the mass at a height h above the ground is given by mgh. Mgh is the potential energy of the mass attached to the flywheel. Then once it started moving down, it started gaining kinetic energy. So the kinetic energy is given by half mv square. Please correct it as half mv square. So then when it moves down, it's try to rotate the flywheel. Okay, because there are number of uh, wounds on the axle. So the corresponding gain, the rotational kinetic energy is given by half I omega square. Okay, so if small n is the number of rotations made by the flywheel when the cord is on the axle. Complete ചുരുക്കി പറഞ്ഞാൽ ഇത് കംപ്ലീറ്റ് ആയിട്ട് അഴിഞ്ഞു പോകുന്നതിന് മുമ്പ് ഫ്ലൈവീൽ n ടൈംസ് റൊട്ടേഷൻ നടത്തിയാൽ then the according law of conservation of energy, the loss in the potential energy mgh is equal to the kinetic energy gain half mv square plus rotational kinetic energy half I omega square plus the other part is the work done against the friction. Here n into w, എന്ന് പറയുന്നത് w is the force against the friction. Okay, w is the ഒരു റൊട്ടേഷൻ കംപ്ലീറ്റ് ചെയ്യുമ്പോൾ ഫ്ലൈവീൽ ഫ്രിക്ഷനെതിരെ വർക്ക് ചെയ്യുന്ന എമൗണ്ട് ഓഫ് വർക്ക് ആണ് w. ഓക്കെ, അപ്പോൾ നമ്മുടെ ആക്സിൽ n ടൈംസ് നമ്മൾ ഈ കോഡ് ചുറ്റുമ്പോൾ ടോട്ടൽ വർക്ക് ഡൺ n ടൈംസ് കോഡ് ചുറ്റുമ്പോൾ n ടൈംസ് റൊട്ടേറ്റ് ചെയ്യുമ്പോഴാണല്ലോ ഈ കോഡ് താഴേക്ക് പോകുന്നത്. അപ്പോൾ n ആണ്, സ്മോൾ n ആണ് നമ്പർ ഓഫ് റൊട്ടേഷൻസ്. അതായത് നമ്മുടെ കോഡ് അതിൽ ചുറ്റി ഇരിക്കുമ്പോൾ അത് ചെയ്യുന്ന റൊട്ടേഷൻ എന്ന് പറയുന്നത് സ്മോൾ n ആണ്. സോ ടോട്ടൽ വർക്ക് ഡൺ എഗനസ്റ്റ് the friction when the cord is attached on the flywheel is small n into w. Okay, so once it is detached, what will happen? So the detach ചെയ്ത് പോയി കഴിഞ്ഞാൽ എന്ത് സംഭവിക്കുമെന്ന് വെച്ചാൽ അവിടെ പിന്നെ പൊട്ടൻഷ്യൽ എനർജിയുടെയും കൈനറ്റിക് എനർജിയുടെയും ടേംസ് അവിടെ ഉണ്ടാവില്ല. കാരണം മാസ് എന്ന് പറയുന്ന സാധനം അവിടെ ഉണ്ടാവില്ല. പിന്നെ ആകെ സംഭവിക്കുന്ന കാര്യം എന്ന് പറയുന്നത് നമ്മുടെ ഫ്ലൈ വീല് കണ്ടിന്യൂസ് ആയിട്ട് റൊട്ടേറ്റ് ചെയ്യും. അറ്റ് ദ സെയിം ടൈം എന്തുണ്ടാവും, അതിന് ഈക്വലൻ്റ് ആയിട്ടുള്ള, അതായത് കംപ്ലീറ്റ് ആയിട്ട് റൊട്ടേറ്റ് ചെയ്ത് തീരുമ്പോൾ ആ ടോട്ടൽ റൊട്ടേഷണൽ കൈനറ്റിക് എനർജി ഷുഡ് ബി ഈക്വൽ ടു ദി വർക്ക് ഡൺ അഗൈൻസ്റ്റ് ദ ഫ്രിക്ഷൻ. ബിക്കോസ് നമ്മൾ അത് റിറ്റാച്ച് ചെയ്ത് കഴിയുമ്പോൾ ഫ്ലൈ വീലിൻ്റെ റൊട്ടേഷൻ സ്പീഡ് കുറഞ്ഞു വരും. എന്തുകൊണ്ടാണ് കുറയണമെന്ന് വെച്ചാൽ ഓരോ പ്രാവശ്യവും ഫ്രിക്ഷനെതിരെ വർക്ക് ചെയ്ത് വരുമ്പോൾ അതിൻ്റെ സ്പീഡ് കുറഞ്ഞു വരും. അവസാനം ഇത് കംപ്ലീറ്റ് റെസ്റ്റ് ആവും when the total energy is used against the frictional force. ഓക്കെ, സോ അതായത് കൈനറ്റിക് എനർജി, റൊട്ടേഷണൽ കൈനറ്റിക് എനർജി എന്ന് പറയുന്ന സാധനം പൂർണ്ണമായിട്ട് എന്തിനായിട്ട് ഉപയോഗിക്കും? n ടൈംസ് നമ്മുടെ ഫ്ലൈ വീലിനെ റൊട്ടേറ്റ് ചെയ്യാൻ ഉപയോഗിക്കും. സോ ദാറ്റ് മീൻസ് റൊട്ടേഷണൽ കൈനറ്റിക് എനർജി ഹാഫ് I omega സ്ക്വയർ എന്ന് പറയുന്നത് that should be equal to capital N. Please remember, capital N is the number of rotations made by the flywheel after the complete detachment of the mass m. Okay, so that is n into w. So from this expression we will get w. So I omega square is equal to nw. W can be calculated as I omega square by 2n. Just substitute in the previous expression omega w ന് പകരം I omega square by 2n substitute ചെയ്യുക. Then you take the half omega square to the left side. So mgh minus half omega square, half mv square. So I omega square ഈ ലെഫ്റ്റ് ഹാൻഡ് സൈഡിൽ ടേബിളിൽ നിന്ന് പുറത്തെടുക്കുക. I omega square by 2 is taken out. It become 1 plus small n divided by capital N, that is equal to mgh minus half mv square. So I will be nothing but mgh minus half omega square into 2 divided by omega square into 1 plus n by n. So on rearrangement, if you take m by 2 outside, the first term become 2gh minus v square into 2n divided by omega square n plus n. But we know v is equal to omega r. Linear velocity v is equal to omega r. So I is equal to m by 2 2gh minus omega square r square into 2n divided by omega square into n plus n. So mb on rearrangement, mb omega square by 2 2gh minus by omega square minus r square 2n divided by omega square n plus n. So calculate cancel ചെയ്യുന്ന terms എല്ലാം cancel ചെയ്ത് rearrange ചെയ്ത് എഴുതുമ്പോൾ what you are going to get is I is equal to n into m divided by n plus m 2gh by omega square minus r square. Now the moment നമ്മുടെ മാസ് ആ ആക്സിൽ നിന്നും ഡിറ്റാച്ച് ചെയ്യുമ്പോൾ റൊട്ടേഷണൽ കൈനറ്റിക് എനർജി മാക്സിമം ആയിരിക്കും. അതായത് ഒമേഗ എന്ന് പറയുന്നത് ആംഗുലർ വെലോസിറ്റി ഈസ് മാക്സിമം, ദാറ്റ് ഈസ് ടേക്കൻ ആസ് ഒമേഗ. ടി ടൈംസ് റൊട്ടേറ്റ് ചെയ്ത് കഴിയുമ്പോൾ അതെന്ത് ചെയ്യും, അതിൻ്റെ സ്പീഡ് കുറഞ്ഞ് ആംഗുലർ വെലോസിറ്റി കുറഞ്ഞ് ഫൈനലി ഇറ്റ് ബിക്കം സീറോ. ഓക്കെ, സോ അതായത് നമ്മുടെ കോഡ് മാസ് അതിൽ ഡിറ്റാച്ച് ചെയ്യുന്ന മൊമെന്റിൽ അതിൻ്റെ ആംഗുലർ വെലോസിറ്റി ഒമേഗ ആണെങ്കിൽ after t times the angular velocity becomes zero. So if you take these two extreme points and if you calculate the average angular velocity as omega plus 0 by 2 is equal to omega by 2. So this omega by 2 is equal to average angular velocity is omega 2 is angular velocity is given by 2 pi f. F is the frequency of rotations, that is number of rotations made per unit time n by 2. So omega by 2 is equal to 2 pi f, where f is equal to n by 2. N by 2 in n by t. N is the number of rotations made in t times. So the f is given by n by t. So omega by 2 is equal to 2 pi n by t, or omega is equal to 4 pi n by t. Okay, you put it back for omega the same expression, and then you will get the final expression for I as nm divided by n plus m gh t square by 8 pi square n square minus r square. So this is the expression for the moment of inertia of a flywheel. Thank you.